and a half to kind of get to that point. I want to talk today, in particular, get us to a point where we can start talking about interactions between atoms, right? Molecules, hydrogen bonds, things like that, right? How do those affect the ideal gas law? So let's start simple. Remember we kind of finished last class, we came up with the ideal gas law. We got it from our statistical interpretation of the entropy. Right, we got this Boltzmann distribution, and I did some kind of math with it that I didn't really go into detail about, but we saw that the Pivner kind of falls out of it, right? What did we find? Well, the first thing that we found, of course, is that for the system at thermal equilibrium at temperature T, that the average energy of the system is 3/2 times the number of molecules times Boltzmann's constant times temperature. Right? And this looks awfully like Pivner if you squint hard enough, right? And we saw that when you look at the pressure of the system at a given volume, you get nRT, right? The ideal gas law. Right? And all this says, right, this is just an equality, right, between two types of energy. Right? It says that for an ideal gas equilibrated at equilibrium, at some temperature in our little equilibrated box, that the amount of energy that you use to fill the box, right, P times V, that's our pressure volume work, right, that's the energy used to fill the box, is equal to the amount of energy supplied by the bath, which is nRT. So the bath energy is equally balanced with the energy of the system trying to fill the box. Right? That's all Pivner says. It's just two forms of energy, and for an ideal gas, they're equal to each other. Right? All the thermal energy gets driven into the work, the volume work, the PV work, and they're equal to each other. Right? That's what it says. Right? And so what does that mean? Well, that means that, right, this is all the energy that the bath gives you. The bath gives you exactly roughly RT, right? nRT times 3/2. There's just some RT. It's just a proportional to RT here. Right? And what this is saying is that 100% of that thermal energy is being put into this, right? But there are other things that the gas can do other than fill the box. Right? So in reality, there's going to be some correction to this to compensate for the other things, or it'll be on this side. Right? This is the energy supplied to the gas. And this is how the energy is used, right? But if the energy is used for other things, right, we're going to have to add additional terms to that, right? Because not all of that thermal energy is being used for PV work. It might be used for attractions or repulsions between the atoms or the molecules. It might be used for electrical work, right? There might be a million different things that the gas might do besides fill the box. But the point is that if the gas is doing that, if it's doing something else, then it's not an ideal gas. Right, so an ideal gas is one that only exists in a space. Right? So that kind of gives us our definition of an ideal gas. It's a collection of non-interacting particles and what does it mean by non-interacting? It means that the only thing they do is just fill the space. They just have kinetic energy that fill a volume with statistics consistent with Boltzmann's distribution, with thermal equilibrium, right? With the fact that the probability of a given energy is proportional to, this is my little proportional to sign. Let me clean it up. It's a little cursive A if you've never seen this before. This means proportional to e to the minus ej over kt. Right, so an ideal gas is just a bunch of dumb particles. They don't have any understanding that there are other particles in them, in the gas. They don't have any clue about anything other than their motion. All right, and all of that motional energy is encapsulated by PV, and the energy supplied is nRT. Okay, so this is a big thing right here, non-interacting. right? That the particles don't see each other. They're not repelled by each other. They're not attracted to each other. And as we'll see, that's not only is it uncommon for that to be the case, it basically never happens. They're always interacting, as we'll see. Right? And I just want to be especially explicit about the conditions of an ideal gas. One is that the particles are point-like. And what that means is they have a mass, they're massive, but have no volume. So each particle in an ideal gas is assumed to be a point in space that has a mass and some momentum. Okay. There's exactly one common particle in the world, in the universe, that satisfies this property. Does anyone know what it is? It's the one point-like particle that exists kind of commonly. Does anyone know? There's a particle that exists in every atom, every molecule, everything, that has no shape or size, but it has a mass. Does anyone know? Yeah, go ahead.
Neutrons?
No, not neutrons. Neutrons and protons have a physical shape and a physical size. It's an electron, interestingly. Electrons have no shape. People have tried for years, decades even, to measure the size of an electron. And as far as we know, electrons have no shape. They're just a point. Okay? Now, the problem is that a gas of electrons are not an ideal gas because they interact with each other because they have charges, right? They have electrical energy. They repel each other. So an electron gas is not an ideal gas, but an electron gas, because they're all negative charges and they all kind of they all interact with each other in an average way, there is an equation for electron gas similar to Pivnert, but we have to account for the fact that there's repulsions between the negative charges. Okay? So clearly no atom is point-like. They all have shapes and sizes. Not all of them even are spherical. The other important thing is that all collisions, right? Because occasionally two of those particles are going to be in the same spot, right? There's going to be some probability that occasionally two particles running around randomly are going to be in the same spot and they're going to bounce off each other, right? So how do we, or maybe they hit the wall. Right? Maybe they hit the wall and there's going to be some bounce, right? So we have to identify what the collisions are, and here we say all the collisions are elastic, right? Which means that they just bounce off each other and no energy change happens. So no energy loss. Okay, so that's kind of like if a car hit another car and they just bounce off each other and move off in opposite directions. Okay? Right? There's no explosion, there's no energy loss, nothing. They just bounce off each other like billiard balls. Okay. And that's basically it. They're not interacting, they're point-like, and all their collisions are elastic. All right? Real gases are interacting, as we'll see. They have a volume, and their collisions are not elastic. Very much not elastic. Okay, but this is just an approximation. All right, so let's see how good that approximation is. So I'm going to graph something, do a little graph. And let's just look empirically at how a gas deviates from the ideal gas law, if it does at all. All right, and the way we're going to do that is we're going to calculate something that is unitless about an ideal gas. We want to think about something that doesn't have any units, right? Something that we can compare like a scale, if you will, a scale factor. All right, so what we're going to do is we're going to define the so-called compressibility factor. Compressibility, that's a big word. Factor. And the letter we use for it is Z. I like to put a little dash in my Z like a Canadian. Sorry, Z, excuse me, that's how Canadians say it. I used to get made fun of for saying Z. It's actually Z everywhere except for America. And the way that we define it is we take the pressure times the volume of our gas and divide it by nRT. Okay, so what we're doing is literally just dividing both sides of the ideal gas law by nRT. Right? And so we should, for the ideal gas, get 1 for that ratio, right? Divide both sides by nRT and you get PV over RT is equal to 1. All right, let me make a few comments about this. Right? So this should be exactly 1 for an ideal gas. Okay. I'm going to define a new parameter just to simplify this, because one of the issues with this equation is that this is size intensive, right? I need to define a specific volume and a specific number of moles for my system in this equation. So what I'm going to do is I'm going to combine the volume and the moles to specify what we call our molar volume, the amount of volume that a mole of material fills. All right, so let me define that. So the molar volume, and the reason why we use this is because I want to get rid of moles. So I want to think of things on a scale and extensive way, right? I want to think about how things change as we add moles. I don't want to care about how many moles I have. I want to think about how things change on a mole basis. So the molar volume, and the book defines it as V bar, is defined as the volume of the gas divided by the number of moles in that volume. Right, so the units of this are, say, liters per mole. Right, and this tells you at a given temperature and pressure, how much volume exactly 1 mole takes up. Okay. So if we double the amount of moles at that, if we want to keep the same pressure in our system, the same temperature in our system, and we want to include 2 moles, then we need to double the volume by 2. Because you need exactly V bar volume for 1 mole. All right, so it's just kind of a specific quantity-independent way to describe the volume. And I just want to add, just in case, this is another useful thing that we'll use later in the class, what's called the molar density. Which is 1 over the inverse volume. So we call this rho. That's the rho, the Greek letter rho, the P. Rho of a bar, this is equal to 1 over the molar volume, right, which is the number of moles divided by the volume they're contained in. And this is in moles per liter. Right, and so this, you can just, again, think of this as the density, right? Instead of grams per milliliter, grams per liter, we just do things in terms of moles instead. Right, so then we don't have to worry about the molar mass and the weight. Right? We can talk about the density in terms of how many moles you can fit in a unit volume. Okay? So they're inverse of each other. Right? And they're useful quantities to measure. Right? They kind of measure quantity. Right? They can measure how much crap you have. Right? It's how much stuff you can jam in a unit volume. That's how much stuff you can jam in a unit volume, or how much volume some stuff takes up. Okay? And we don't have to worry about how many moles we have or how much grams we have, because that's all carried into the molar part of the equation. Okay? So let's look at what I'm going to do. I'm going to make a new slide, if that's okay. Are we all good so far? Okay. What I want to plot, all right, I'm going to go into the lab. Right, and this is something we could technically do in lab if we wanted. I'm going to plot a plot for different gases of the pressure of the gas. Sorry. So on the x-axis, I'm going to plot pressure. I'm going to write it in terms of bar. Remember that 1 bar is approximately 101,325 atmospheres. So it's about an atmosphere. Okay. And on the y-axis, I'm going to plot z or z for that gas, the compressibility factor. Okay. All right. And let me just make some pretty marks. Let's make my graph. I got to give it a little more space here. I'll write this again. I just want to make some tick marks. So 0, we'll run it from 0 to 1,000 bar. 200, 400, 600. 800. And this is pressure. Okay. All right, and we know for an ideal gas, if the gas was perfectly ideal, the value is 1 for all pressures, right? So let's put that here on the graph, 1. Right, so this little dashed line, which just goes straight across, I'll just make it a straight line, is an ideal gas. Okay, so if our gases are perfectly ideal, they're always going to give the same value regardless of the pressure. Okay, so let's try, right, that's our assumption, right? This is our approximation, if you will, right? We expect this. So how do actual gases look like from this point of view? Okay, so let's try a really simple one. Let's do helium, all right? So yellow is going to be helium. And what you find is at low pressure, it's very close to, let me do a different color because I have the yellow on the graph, so I'll do purple for helium. So helium, again, at low pressures is basically perfectly ideal. But let me add a couple more tick marks here on the right, just so I know where to go. Okay, so we're ranging from 0 to 2. Is that this slowly increases linearly It's not the best graph in the world, but it slowly increases linearly to the positive as the pressure increases. Okay, so for helium, right, it says for large P, it says that Z, which is equal to P times the molar volume divided by RT, is greater than 1. All right, so what does that mean? Right? Well, it says that this quantity, remember P times V, that's an energy. It's work. All right, it says that the energy that's required to fill the box, the energy available to fill the box is greater than what's being provided by the thermal energy. All right, so what that means is that there's some additional force acting on the helium to fill the box, a positive energy. Positive force is being applied by the gas to fill the box. That's more than the energy given to the system by the temperature, by the bath. Right? So what this means is there's some positive non-thermal force pushing the atoms apart. It's getting a little extra kick from something to fill the box. There's an extra work kick happening as the gas fills. All right, very interesting. All right, so let's go to a little more interesting gas. Let's do N2.
I have a question.
Yeah, go ahead.
Can you reiterate why you know that there's some positive non-thermal force pushing? 'Cause like if
Oh, good question. So again, think of this as a balance of energy,
Okay.
right? So this is the energy in from the bath, and this is the energy you read from the gas from how it fills the network that it takes to fill the container. Okay? So for an ideal gas, they're equal to each other, right? Every unit of thermal energy that you put in gets put into the work. Right? So this energy balance would be 1, right? Would you agree with that, Monica?
Yeah.
All right, so if it's greater than 1, that means that there's an additional piece of energy in the numerator that's being added to the work that isn't coming from RT. It's an additional chunk. Right? You could kind of say that maybe a better way to think about it is that Z for helium looks a bit like the PV, which is the ideal part, right? Which is just the nature of the gas pushing against the walls, plus some additional energy from something else divided by RT. All right, and we have to identify what this additional energy is. Right? There's something else adding something to the system, right? There's an additional force in the system besides just thermal effects. Does that answer your question?
Yes, thank you.
You're welcome. Okay, so maybe it's worth looking at how this changes as a function of the gas. Right? And that's what you're doing in lab this week, right? We don't just do one gas, we do a couple different ones. So let's look at nitrogen. Nitrogen's very interesting. I'm going to do it in like a magenta. Well, it's not really interesting, but it has similar behavior. It stays flat for a while, but then as pressure increases, the compressibility factor increases even more. Right? So for N2, right, at 800 bar, right, these are really high pressures, right? So again, in lab, in the Joule-Thomson experiment that you're doing, the pressure you're working at is about, at max, 60, 80 psi. That's about 6 or 7 bar. Right? So the place you're working in lab is like right here. Right in this section right here, right? So these are really, really high pressure effects, right? Right? You don't really see a huge change until you really, really, really pressurize the system. All right, I'll just remind you of that. I'll just put that here. This is, all right here, this is the lab world. Oops, sorry, I zoomed out. Right. Okay, so there, most of the gases like kind of look the same, and they're mostly ideal, right? Low pressure. All right, so there's something in N2 that at low pressure causes it to stabilize more relative to helium, right? There's some, right? If you think about in this region right here, right? Nitrogen has something else is happening to nitrogen that causes the Z not to increase that fast, right? So compared to helium, something else is going on in nitrogen here. But once you pressurize the nitrogen, now remember nitrogen is bigger than helium. Helium is just an atom. N2 is 2 atoms together. They take up more volume, right? And so as you get to higher and higher pressure, that volume of the nitrogen, if you will, is starting to cause some effect of pushing the gas away more than you would expect. Right? So there's like 2 effects maybe going on here, right? There's something that has to do with the identity of the gas and how repulsive or how much it pushes at high pressure. But there's also something here that distinguishes the gases at low pressure as well. And we're going to see that in just a second when I add my next gas to the list. So let's go up in complexity from N2. All right, let's make it a little more interesting, and let's do methane. All right, you may say that's not that much more interesting, but methane is a far more complicated molecule than nitrogen. You can do a whole PhD, you could do your whole career studying methane. Very interesting molecule, sorry. And what happens in methane is very interesting. I think I've said that enough, I'll do it in orange. Is that it has a negative deviation at low pressure. So methane decreases like this, and then it starts to track similarly to N2. Okay, so this is why I'm saying there's a balance of effects here, right? At high pressure, there's something that's driving the system, pressing the system out, right? It's causing the system to press against the walls harder than you would expect, given the temperature, right? But there's something that happens at intermediate pressure here where the opposite happens, right? There's something that's going on increasingly from helium, as we go up in complexity, if you will, from helium to nitrogen to methane, there's something that's happening in this region that is opposite to what happens at high pressure. Okay, so there are regions, right? So we see that there are some regions, so if Z is greater than 0, greater than 1, right, we have something pushing the gas away from the center. Right, Z of 1 means the gas is being pushed outwards relative to an ideal gas. But Z less than 1, Z less than 1 means the opposite, right? It means that RT, the energy supplied from the exterior, the thing that's giving you temperature, that energy is more than what is necessary to fill the box, if RT is greater than PV. Right? So that must mean that there's some negative force, right? Some force that's pulling the system away from the walls if Z is less than 1. It's the opposite effect. So Z less than 1 means that there's some of force pulling gas inwards. Okay, it might be better to try to think about this on a gas-by-gas basis. And instead of changing pressure, let's fix the pressure. No, sorry. Let's look at a single gas, but let's change the temperature and see how this changes, right? How does temperature affect this result? These are all done. I think these are all at 298. I should have said that. Sorry, guys. These are all at 300 Kelvin. So all of these are at T equals 300 Kelvin. Okay, room temperature. All right. So it may be worth thinking again. So what we're doing again is we're monitoring P and how Z is changing. But let's see how Z changes as we change T. Right, how does the temperature, the energy applied from the outside, affect the behavior of the gas? All right, so let's make a new plot. Same plot as before. Run it from 1,000 to 0. I need to spread these out a little bit, sorry. Maybe like right there. That looks good. 600, 800. Okay, and then this is pressure, of course, on the x-axis and bar as before. And we're going to plot Z on the y-axis, and we'll vary it between 0 and 2 as before. All right, and let me just redraw my ideal gas plot. All right, this is ideal. All right, it's just nice to have that comparison. And I'm going to look at these curves, these pressure versus Z curves, as a function of temperature for methane, right? Because it's clearly methane is the one that's interesting, right? Because it's the one that goes negative. Right? It's clearly got two different effects, one at low pressure and one at high pressure, a negative deviation and a positive one. So let's see how that varies as a function of temperature. All right, so I'll kind of redraw the 300 Kelvin one. So it kind of goes like this. All right, this is 300 Kelvin. All right, that's what we saw on the previous slide. All right, let's go down temperature. Right, what happens when I cool the system a little bit? Well, what happens is that negative deviation sparks even more. And then it actually climbs faster as pressure increases. Like that. All right, and then as we heat the system more and more and more, the deviations start to level out a little bit. So at 400 Kelvin, find a color for that, we'll do blue. For 400 Kelvin, the system barely deviates negative. And then it grows, increasing more slowly than 300 Kelvin. Right? And then for 600 Kelvin, the hottest temperature that I have on my data, it barely deviates at all negatively. And it grows more slowly than the other ones do as well. Okay, so what do we see from this behavior? Well, it shows that as temperature increases, the system starts to act more ideally, right? I mean, it still decays, it still deviates, right, quite a bit, but it decays, it deviates less, right? Z doesn't get as positive as fast at high pressure, nor does it get as negative at low pressure. But as you start to drop the temperature, right, as you start to pull thermal energy out of the system, the deviations become more extreme. So what can we say about this? One, it says that, right, what are some observations we can make? One, it says, is as T increases, gas acts more ideally. Okay. And two, as T decreases, deviations become more extreme. Okay. And it seems that deviations depend almost entirely on pressure. Strongly on pressure. Okay. All right, so actually we can generate what we call a limiting law from this. Right? That we can kind of put all of these together. That ideality, when we say something is ideal, we're talking about the properties of a material at the limit as T goes to infinity and pressure goes to 0. Right? So a perfectly ideal gas is one that is basically there's infinite distance between each of the atoms in the gas. So the volume is massive volume or small pressure, and it's really, really hot. Okay. So ideality only happens at these two limits, right? Or both. Ideally both. But we can take a gas at any temperature and bring the pressure to very, very small pressures, and then we get ideality back. Or we can take something at very high pressure and heat it up and get ideality back from it as well. All right, and again, this is just the balance between the amount of energy being provided to the system to do work, right? PV. So as V gets bigger, you're doing more and more and more work to fill that box. So that this gets big compared to whatever this is, this little deviation in the energy for big pressure. Or if you have so much temperature, so much thermal energy, delta E is small compared to it, the correction is small to it, and the thermal energy just dominates. Right? And you just get Z equals 1 back. Okay? What I want to do today is to identify where this is coming from. Okay, what is causing these deviations? They're clearly in some ways dependent on the material. Right? Not only are they dependent on the pressure and the temperature, but they're obviously dependent on the material. Right? Methane clearly has more dramatic deviations than the other two. What I want to say is that the sources of these deviations are exactly the same. Right? They all share the same mechanism in common. The characteristic of the material, chemistry of it, if you will, the chemical properties of the material ultimately determine how great these deviations are. But the fact that they exist at all in their trends don't have anything to do with the material. They have to do with just laws of nature, because we see them for everything, and it's just clearly that the magnitude depends on the properties of the material, not the existence of the deviation. All right, so I want to focus in on that universal quality of this, right? What do all three of these things share? All right, in order to do that, I want to tell you a story from physics that I think is very, very instructive. All right, this is a really famous experiment that was proposed in the 1950s or the 1960s, but it wasn't done until the 1990s. Okay, so it took them 30 years to be able to do this experiment. But the result was predicted almost 40 years before. And the experiment is very hard to do, but the idea is very simple. All right, what I'm going to do is I'm going to take two metal plates, square plates. Let me not draw that like I have Parkinson's. Hold on. All right, so I have this metal plate here. I think it's aluminum. All right, so this is a metal plate. It has area A. Say it's aluminum. And area A. Okay. And let's just say it's mounted straight up. Okay, so it's completely straight. Completely straight. It's mounted to like a little post here. And mounted to the ceiling. All right, so you have this fixed plate. Okay? And what I'm going to do is I'm going to introduce another plate, another metal plate, identical plate, parallel to it. Okay, so I'm going to stack them like this. All right, they're going to be perfectly parallel to each other. So I'll draw it with a different color. All right, there's my other plate. Let me fix that last. That was depressing. There we go. So I got two plates. Pretend that they're the same. They're the same plate. All right, and I'm going to separate them by a distance L. All right, so the middle of the plate and the middle of. Let me just mark them. All right, so the middle of this plate is this little dot, and the middle of the other plate is this yellow dot. And I'm going to measure the distance between them by L. These are these are parallel. They're parallel plates. And the important thing is that they're electrically neutral. Right? They have no charges, there's no voltage running through them. They're completely isolated. All right? They're as boring can be. All right? They're the most boring aluminum plates you've ever seen in your entire life. They have nothing interesting about them. They're completely flat. They're parallel to each other, and we put them at some distance L. All right, and then what I'm going to do is attach the orange plate to a spring. All right, so think like a slinky or something like that, something that has a restoring force. And I'm going to mount that onto a brick that doesn't move. All right, so this is a spring. Okay, and what's going to happen is, for instance, if something causes this orange plate to be attracted to the other one or repelled, right, you bring these two plates together, if there's any force between them, if there's any force that's felt between the two plates, the spring will move, right? Because the orange plate, if it's attracted to the yellow plate, it's going to want to stretch the spring. If it's repelled, it's going to want to compress the spring. Right? So I'll just write that. So the spring compresses if plates repel, and it extends if plates attract. Okay. All right, again, these are just very boring aluminum plates. Okay, so someone did this experiment, right? And they asked the question is there any sort of net attraction or repulsion between these two boring metal plates? Okay, there's no voltage between them. For instance, if I were to apply a positive voltage to this orange plate and a negative one to this one, they would be attracted. Positive, negatives attract. Right? So I have electrical current running through them, right? They'll create a circuit. Right? And the circuit means that there's going to be some electrical attraction between the two. All right? That's not happening here. There's no electrical intervention. Okay? These plates are just as boring as this piece of metal right here. Right? Not doing anything. And so they asked the question, what is the force felt by the spring as a function of the distance? Is there any force? All right, so what is the force felt? So what we'll do is we'll plot as a function of L, the distance between the two plates, the force felt by the plates. All right, and I'll make it positive and negative. All right, so 0. So if it's a positive force, Let me make sure I have this right. Yeah, if it's a positive force, this means repulsion. All right, the plates repel each other. And if the force is negative, that means they attract each other. Okay? So the force, you can think of the force being acted on in this direction. All right, so we're measuring this way. I'll just write that. Right? So the force is in this direction. Okay, so they bring these two plates together and they try to get them as close as possible. All right, I'm going to let the area of the plates be 1 square millimeter. All right, tiny little plates, okay? And I'm going to range the distances between 1 nanometer. Let's just do it in terms of 10 nanometers, 100 nanometers, and 1,000 nanometers. All right, so we're going to bring them really, really close together. Right? And what do you see? Well, it turns out that when the plates are really, really far apart, there's no force, right? Go try it at home. Go take two aluminum plates or any pieces of metal you do and put them next to each other. As close as you possibly can without touching them, you're not going to feel anything. Right? It's not. You've probably inadvertently tried this experiment before and you never felt anything, right? They don't attract each other. But as you start to bring things in towards 10 nanometers, the system starts to attract. In fact, at 10 nanometers, the net force is macroscopic. It's about -1 newtons. It's about 0.8 technically. And so as you bring these two boring plates together, nothing's going on between them. There's no reason for them to attract each other from classical physics, right? They have no electrical current, nothing at all. They're just boring plates. But what you find is that that they actually attract each other as they come closer and closer and closer together. And in fact, they come together exactly with the formula that they predicted 40 years ago, which is that the force acting on the system, on the spring, divided by the area, is equal to minus Planck's constant times the speed of light, pi squared, divided by 240 times the length to the 4th power. Okay. This was predicted 40 years ago that if you take two plates together, that in fact they attract each other. And they attract each other as 1 over the length to the 4th power. And that's exactly what you see, perfectly to 1 part in 1,000, or however precise that they measure it. All right, it's a perfect agreement. Now, what the hell is happening with these two boring-ass metal plates? How the hell can they attract each other? And it doesn't matter what material you use. If you can do it with Teflon. You can do it with any material. Take two plates of any material. In fact, they've done it with spheres even. Bring two spheres together. It doesn't even have to be a plate. And you find that they attract each other at very close distances. As you start to get to microscopic distances, right? 10 nanometers is not very long. It's about 100 chemical bonds long. Not very big. So they're super, super close together. And they have a net attraction, a net macroscopic attraction. Right? That's something you can measure. Right? This is about the force. This is the weight due to gravity of an object of about 100 kilograms, or 100 grams. Right? It's the force due to gravity on 100 grams. Right? So it's a real attraction. But where does it come from? It's a very interesting question. Well, the explanation is quite interesting. If you think about these plates, let me redraw it. You think about these plates, right? What do we know about metals or any surface, right? On the surface of any metal, right? There's what Paul Dirac calls a sea of electrons. Right? There's what's called the electron seat. So it's all these electrons that are floating on and the outer orbitals of the aluminum atoms, you know, in the d orbitals and stuff. And they're all connected. All these atoms, all the d orbitals are aligned, and the electrons are allowed to flow through them. So there's this like current of electrons, right? You have this flow of electrons. Right? And you can kind of think, right, the electrons are flowing through this system, but the net field, the net flux of electrons is 0, and the electric force is 0. So it all cancels out. So it does a big loop. Right? So what I really should do is connect this back. Right? The electrons are just moving randomly, but they're just moving in loops. All right, maybe there's another electron in here doing this. Maybe there's another electron in here moving around like this. Right, you have all these electrons moving around randomly. All right, the electrons are moving randomly. They're thermalized. Electrons on surface are thermalized to 298 Kelvin or whatever the temperature is, and move randomly accordingly. All right, just think of like an electron gas, a gas of electrons accordingly, but they're stuck to a surface, right? So instead of having a three-dimensional box, we have a two-dimensional plane of these little point-like particles moving around randomly in circles. And the net flow is 0, so there's no voltage, right? There's not a flow in this direction or this direction or this direction or this direction to apply a voltage or a current across a bit. So all the motions cancel out. Okay, so now what happens when you bring the other plate in? All right, so as you bring in the other plate, and again, I'm going to kind of screw this up, but that's okay. I bring the other plate in at distance L, right? And this has got electrons moving in random directions as well. Same properties, right? And so on and so forth. But as you start to bring them together, right, the average of the voltage across both of the plates is 0. But when you bring these close and close enough together, you may have a slight fluctuation in how the electrons flow, right? So as this one starts to get, as the new plate starts to get closer, it may cause the electrons to jiggle a little bit. They might move differently. Right? So as second plate, we do a different color, approaches first, plate, the random motion of electrons on plate 1 are slightly influenced by the motion of the electrons on 2. Right? So imagine, for instance, you have this orange electron on plate 1 moving in this direction, and then this electron on plate 2 in olive is moving in the opposite direction. Right, so you have one electron going like this, counterclockwise, and the other one going clockwise. Right, that may cause one of the electrons to right, they want to repel each other. So let's imagine they're both going clockwise. All right, maybe that's better. Right, so we have an electron going this way, and an electron going this way. All right, and you bring them together, the plates together. All right, remember, electrons want to repel each other. So as this electron wants to move in this loop, this other one is moving kind of coincidentally with it, randomly. and they want to move, they want to repel each other, right? So instead of them moving coherently together like this, right, they're going to stagger each other a little bit, right? So they're maximally far apart from each other, right? So initially it would be like they're in phase, right? But they want to be extended as far apart as together, so that what happens is the second plate comes in, they try to dephase a little bit, and let's say this electron's going like this on plate 2, and this electron's up here, right? So now they're like this. Okay, so imagine that happening to all the random motions, right? That all of the random motions on this plate want to compensate for the random motions of the plate nearby, because those electrons are interfering slightly. Okay, and so what you find right, you find that the average flux of electrons, or field, the average flow of electrons across the plates from 1 to 2 is equal to 0, right? Because they're electrically neutral. There's no net voltage, there's no current, right? No current. But there are times, but that's on average, but there are times, random times, where one of the electrons might screw up its random velocity and cause a little instantaneous voltage because it wants to get away from one of these. Right? There might be these little instantaneous motions where the electrons have to move that isn't random. Right? It's not a random motion because it's got to get away from one on plate 2. So when you look at the statistics, so the average of the flux is equal to 0, but the standard deviation of the flux, the variance of the flux, so this is the variance, is not equal to 0. Okay, so on average, there's no electron transfer between the two plates, but there are occasional fluctuations in the randomness that cause a really quick instantaneous voltage. Right, so what's happening now, what does that mean? Well, that means is that if we were to plot the voltage, for instance, as a function of time, right, so if we take time and then plot the voltage between the plates, we would see it oscillate very, very quickly. Right? It would look like that. Right? And what's the average of this? Right? What's the average of this voltage? Well, it's 0 because it's above the, it's positive just as much as it's negative, right? So the average of this voltage, right? So it says here the average voltage is 0, right? Because a sine wave is above 0 as much as it's below 0. But the standard deviation in the voltage is not equal to 0. And it's not too hard to calculate, but the standard deviation of a sine wave, which is called the root mean square displacement, is like right here. Right, so this is sigma v. Right, it's slightly positive. Maybe that's squared instead. Okay, so what does that mean? Well, it means on average the net voltage between the plates is not 0. There's no interaction between them. But occasionally, on the edges, every once in a while, you have a voltage swing, because one electron on one plate influences the other one. Okay. What does that mean? Well, that means that on average, again, no net flux, no net electrical energy, but there is these little instantaneous random events that occur statistically in the system that cause it to have some non-zero value. Right? The fluctuations of the system cause the voltage to have a non-zero value when you look at things in quadrature. Right? When you square everything. You square things, the average of the square is not equal to 0, but the average of the value is 0. That's what this is saying. So the square of the voltage is non-zero on average, but the average voltage is 0. So what that does is it means that it induces a net effect, a net attraction on the system. There's a very, very small, as you can see, very, very small, almost minuscule effect. But this leads to a net attraction, a net interaction between the two plates. right? Because there's a net fluctuation of the electrons between them that are influenced by each other. They know each other are there. On average, they don't, but occasionally they do. And that occasional fluctuation leads to this very, very small net interaction. All right? This has a name. Right? This is what's called the Casimir effect. Casimir effect. Okay, now you're probably wondering why I've just spent 20 minutes talking about two metal plates when we just talked about gases, right? So how does this connect? The story connect to our gases? By the way, I don't think Casimir won a Nobel Prize for this, unfortunately. It's a really beautiful piece of work. This effect is universal. It's got nothing to do with the metal plates. The reason why experimentally they use metal plates is because it's really easy to make two metal plates parallel and bring them close together. Okay, but they've shown that you can do this with two metal spheres as well. Right? It's independent of the geometry. It's a universal effect. It's only related to the distance between these two balls of electrons. Only depends on that. So it's completely universal. All right, so let me go to the next page real quick. Let me copy my plates over because I want to draw them. You don't have to redraw them yourself, but I just want them for my picture. Just want them for my slide. All right, so we call this net attraction between two plates attractive force between two plates. This is the Casimir force. All right, what if I replace these two plates with heliums? What if I take two helium atoms and separate them at a distance L? All right, same idea. Bring them close together. Do we see a net attraction? In fact, we do. Same effect, attractive force. But we give it a different name. In chemistry, interestingly enough, chemists have determined this force, or rather people who are interested in chemistry knew about this Casimir force in atoms and molecules before it was ever standardized, right? The Casimir force is the universal effect. But this effect was known for two gases, neutral gases attract each other or repel each other. They have attractions or repulsions. And the mechanism is precisely the same as it is for the two plates. There's a couple of different names that we give this. Traditionally, it's called the van der Waals force. Another term which I'll use interchangeably is called London dispersion force. All right, those are the two common names for it. All right, you guys probably learned about van der Waals attractions or London dispersion in intro chemistry. The cool thing about London dispersion forces is, again, the van der Waals or the London dispersion force, the attraction between two atoms or two molecules instantaneously is the exact same thing as the Casimir force, except it's done with atoms or molecules instead. In fact, we can actually make a very important claim that given the right conditions, all chemical matter, actually all electronic matter, anything with electrons, is attracted to itself, or is attractive to itself or others. Everything. All right, I can even, in quantum mechanics, if we have a little bit of time in class, I can prove to you that regardless of the atoms chosen, materials chosen, put the two things at the right distance, they always attract each other. Now they might not attract each other much. As you might know, helium isn't very attractive to anything. Noble gases are noble gases. They don't form any bonds except for xenon and krypton, the bigger ones. Helium obviously doesn't bond to anything when it's neutral. But helium and helium are attracted to each other. People have even studied it. They've even measured the strength of the attraction between two helium atoms. So heliums naturally attract each other. All right, I want to show you an interesting model of how we model these van der Waals attractions in chemistry. All right, so we have a useful model. For chemical or atomic van der Waals attractions. All right, it's called what's called the Lennard-Jones potential, named after two men, Leonard and Jones. All right, it has a really, really simple formula. All right, so this is the potential energy of the attraction. It's a function of the distance between the two atoms, L. And it's equal to 4 times this number epsilon. I'll explain what these numbers are in a second. Let's just write it down. Times this number sigma over the distance, all to the 12th power, minus sigma over the distance to the 6th power. Okay? So it turns out this is a really, really useful model, and it qualitatively works very well for understanding the energy, potential energy of attraction or repulsion between two atoms at a given distance. Okay? And it's parameterized by two things, epsilon and sigma. Right, and I'll show you what those are in just a second. So epsilon, they kind of have generic labels. Epsilon is called the interaction strength. Or the well depth. How deep? I'll show you why it's called a depth in a second when we plot it. And of course, this has units of energy, right? Kilojoules per mole. Right, some energy. All right, and sigma is what's called the length scale of the interaction. And it has units of meters or angstroms, whatever you prefer, length. Okay, so what are the units of this equation? Well, sigma has units of length. Length divided by length is unitless, so this whole thing is unitless. It's multiplied by a number times kilojoules per mole, so this is in kilojoules, or some sort of energy. All right, so this tells us something about the energy of the attraction or the repulsion. We'll see which one it is in a second, as a function of the distance between the two atoms. All right, I'll just plot an example for you. So what I'm going to do, actually, I need a little more space than that. Sorry, guys. I need this needs to go negative. Do it like that. And I'm going to plot L on this axis and the attraction energy V on the y-axis. All right, so let's think a little bit about how this function trends depending on the value of L. Okay? All right, so let's think about L close to 0 first, right? What does this curve look like at small l? Well, you've got a small number in the denominator, so sigma over L is going to be large, and you're taking it to a large value. And so we have some big number to the 12th minus a big number to the 6th, so this is positive. This is positive. So the whole thing is positive, and it gets bigger and bigger as L gets smaller. Right? So it grows really fast like that to infinity. Right? What happens at limit L goes to infinity, right? When they're infinitely far apart? Well, this is just 0 minus 0, it's 0. So at long distance, the function goes to 0. All right, and in between, it actually dips down below 0 and then loops back up like this. Like that. Let me clean up the top part real quick, make it smooth. Yeah, good enough. Like that. Okay, so what does this say? Well, it says that, right, so at distances smaller than this point right here in purple, right, in this region, right, in this region, V is greater than 0. What does that mean? Well, that means that what's happened now is you've brought the atoms in so close together that they push each other apart. Right, so this is the repulsive well of the fact that when you have two atoms so close together, their electrons start to get really close to each other. Right, you bring them really, really close, they want to push away as the electrons start touching. Right, so we have this repulsive region right here, positive energy. Right, so this is the repulsive wall. Right, this is like where you have an atom and you have another atom just butting into its space. Right? And then we have this region out here where way out here, no attraction, no interaction at all. Right? That's where the atoms are so far apart they don't even see each other. Right? And then there's this Goldilocks region in the middle where it's negative. Right? And there's this magical point right here, right, where the interaction energy is most negative. Sorry, let me erase that. I need to match it. Right? There's this point right here, right? And this point is minus epsilon. Right? And this region right here is where the two atoms actually like to sit and hang out close to each other. There's a net attraction. Okay? And the strength of that attraction is epsilon. Okay? So the stronger the two gases, that's why we call it a well depth, right? Because as a function of distance, you drop into this energetic well. Right? The energy goes negative, right? Which means a stabilizing force. Right? This is repulsive, positive energy, wanting to push the system out. Right? And this is an attractive force, it's a negative energy bringing the system together. And there's this net attraction at this epsilon. Right? And the point at where the kind of the natural length of this attraction is, right? This natural point where the energy attraction is maximum, turns out to be at a kind of a specific strange value, but it's not too hard to figure out how. 2 to the 1/6 power times sigma is this point right here. All right, so sigma tells you something about, again, the length scale of the attraction, right? How on average do the two atoms like to sit together? So sigma tells you something about the length scale, and epsilon tells you something about the well depth, how strong the attraction is. Let me give you some example numbers just to kind of give things in perspective. I don't have them here, I just got to pull them up. Oh, yeah, here we go. Excellent. Okay. So for helium, I don't actually have helium's numbers here, but let's just look at some ones. So for nitrogen, sigma. Sorry, this is sigma. All right, this is a bad plot. Let me start over again. Sorry. So we have sigma here, and I'm going to do it in units of angstroms. And the well depth, epsilon. And we'll do it in kilojoules per mole. I got to do a conversion here, so let's do N2. So the distance between two N2 molecules on average is 3.163 angstroms. Just as a reference, if you don't know what an angstrom is, I'm just going to put it down here. 1 angstrom is 1 times 10 to the minus 10 meters. Okay. And the distance between a carbon-carbon single bond, the CC bond is about 1.5 angstroms. Okay, so 1 angstrom to 1.5 angstroms is like a good kind of chemical bond. So these two nitrogens like to sit at some distance that's almost over 2 to 2.5 times the chemical bond distance between the two atoms. All right, and their strength. Again, I have them in Kelvin here, but I'm going to convert them to kilojoules per mole just to make your life easier. Yeah, 100. Okay. So the interaction strength is 100 Kelvin. All right. Yeah. It's very, very small, 0.83 kilojoules per mole. All right. The average bond, carbon, okay, so let's just compare to carbon-carbon. All right. So the length of carbon-carbon is about 1.5 angstroms. The bond strength of a carbon-carbon bond is about 400 kilojoules per mole. Okay, so the average covalent bond, you should think 250, 400, 500 kilojoules per mole. And so usually the attraction, the length scale of a bond is about 1 to 1.5 angstroms. Say 1 angstrom. Right? So this is a very, very long attraction, very long distance, long range, and very weak. Very weak, but it's non-zero. All nitrogens attract each other this way. All right, let's try a different one. Let's look at methane. Methane, again, not really that much different in terms of its distances, but its strength is quite a bit more. Let me just get the right value for you. .3 kilojoules per mole. Okay. And I can find heliums because those are the 3 gases we looked at, so we might as well have them for all of them, right? All right, so for helium, the distance is 2.5 angstroms, and epsilon is about 0.7. Okay, so what's happening here? Well, remember our trends when we looked at the compressibility factor, right? Remember, methane was the one that had the most negative deviation, and then nitrogen, and then helium. We're almost done, I'm sorry. Right? And you can see that these are now correlated. Methane has a significantly higher attraction to itself. What we're going to see, we'll talk about this on Monday, that the reason why there's that negative deviation is because what's happening is the helium is clustering together. It's attracting itself. You're not individual atoms, but you have clumps of helium, or clumps of methane, because they're attracted to each other. Right? And likewise, nitrogen and helium aren't quite as useful at that because the attractions aren't nearly as great. So those negative deviations that we're going to see are due to attractions, and the positive deviations in our curve are going to have to do something with the repulsion of the system. All right, where they try to push each other apart. Okay, we'll look at this on Monday, guys. And then we'll talk a little bit more about attractions and interactions for other molecules.
Can I ask a question?
Yeah, ma'am.
I mean, this is just picky, but for N2, is it 361 or 13? Because you said 13, but you wrote 61.
It's 3.6, almost certainly.
Okay.
3.1 would be too short.
And then, so, I was a little confused when you were saying, so why are you doing the sigma squared?
Oh, think of it like this. So on average, you don't see a net change.
Just to make it more like apparent.
Yeah, but the thing is, it's the difference between the mean and the root mean square. Right. So if you have a system that oscillates so quickly that you just average over all of them, it's always at zero. But if you just have a system that oscillates more slowly,
Yeah.
if you check at different times, the voltage is going to be off a little bit, right?
Yeah.
Imagine every time you check, you might be up a little bit, you might be a little below in your not in your sample, not your population, right? So if this, imagine this oscillated infinite frequency, and if you were to measure it on average, basically every time you're going to hit zero, right? But imagine now it oscillates more slowly.
Yeah.
And you make those, constant
Yeah.
time measurements. Sometimes you're going to be above, and sometimes you're going to
That
be
makes
below.
sense.
So your mean is still zero, but the value is fluctuating. So because there's a fluctuation, it turns out there's a net force that arises from that fluctuation, because you have a little bit of force coming from the positive and a little force coming from the negative. And we take the quadrature, it's the square. So you square the sine wave, so it's always
To make it
positive
so it's more.
because it's a square function, right, in quadrature. And so if you think about if it's oscillating slowly from 0 to 1, 0 to 1, on average you're going to measure it somewhere around 0.5. Right? And because when we measure the force, we take the square, but the field isn't oscillating, so the field
So it
strength
makes
is
it
0.
0.5, not 0.
Yeah, so our observation is non-zero, but the field strength is on average 0.
Okay. I have one other thing, but I'll hold on to it.
Yeah, give me just a minute, or if you can wait, let me just close up shop, give Matthew his computer.
What class is in here after? What do you teach? What class do you teach?
Mergers and acquisition.
Cool. I don't know what that is.